work, and recently, within the last year and a half, joined the materials department here at UCSB. And she's really doing some exciting work on interfaces. So the lollipop that you may have seen on the Materials Monday advertisement slide was alluding to something that Angela, I think, will talk to us today about interfaces and wear, and how materials, when they're in contact with each other, change. And so this is a topic that's, of course, very important in real life, and it's something that's very important to the materials department to research and to understand and be able to use in various new ways. So with that, Angela, we're really looking forward to your talk, and the floor is yours.
Thank you so much, Chris. I am so glad to see everybody here. I'm just making sure we're recording. Perfect. For those of you who had internet issues earlier today because of the storms, you can watch this later. So yes, thank you again for the introduction. My name is Angela. Please don't hesitate to interrupt with questions if you have any. I'm happy to answer any questions, any and all questions. So without further ado, I'm going to try to share my screen and show you this presentation. This is my first time doing a PowerPoint presentation, so bear with me. Let's see if I can put it onto the presenter mode. Can everybody see this?
Yes, we can.
All right, beautiful. And it's coming out clear and everything?
Beautiful.
Beautiful. All right, great. So today I really want to talk again about how interfaces are really important, not just in the scientific community, but also in our daily lives. And so if you have ever had a chance to have a Tootsie Roll pop, like the one shown here, you'll know that part of the experience is to eventually get to the center of the Tootsie Roll pop and enjoy it. And I'm sure many of you have seen the age-old cartoon from the 1970s.
How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? A good question. Let's find out. 1, 2, 3. Can't stand. It's a smart owl. How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? The world may never know.
Well, that was the 70s. Obviously, a lot has changed. Oh, no. Okay. A lot has changed, and now we are driven by very simple questions to solve deep, fundamental problems in physics. So today we're going to find out just how many licks it takes to get to the center of a Tootsie Roll pop. But first, let's take a look at one of our interfaces. So this Lollipop interface is two-component, arguably. The first is yourself. You are part of this interface. You are licking a lollipop. And the second part of the interface is the lollipop itself. So we went through and we took a bandsaw and we cut a whole bunch of the same type of Tootsie Roll pops. These, of course, are trademarked. I'm just going to call them lollipops for now. But each of these cross sections, you can see that this is the little stick that goes through the center, and these dark regions that I've highlighted with my mouse right here, this is where the Tootsie Roll exists. This is like a chocolatey kind of center. It's very chewy, and this is the core of this treat. Surrounding this core is, of course, the lollipop itself, and the lollipop has this red coloration to it. It's dyed. It's mostly sugar and very sweet and tasty. This is what we want to eat. So 2 parts. This is a composite material, if you will. And the very first thing you might notice is that these surfaces are highly irregular. So the question of how many licks does it take to get to the center of a Tootsie Roll pop is surely dependent on what direction you start licking, right? Because you can imagine if you start licking right over here at this corner, you might hit the center, quote unquote, pretty quickly. Whereas if you start on the opposite pole or another spot, you're not going to make it very quickly. You're going to make it after many number of licks. So let's take a closer look at this. How do we solve this problem? So let's take a journey to the center of the lollipop. And before we do so, I just want to call out a few points of interest. So again, we've called out this center region, which is the soft, quote unquote, center. Center of course, is in quotations, because even though it's advertised as the center, it's very clearly not centric. It's acentric. It's asymmetric and highly irregular. And so this is your soft center surrounded by your hard candy. And here are some typical dimensions. And this is again a trace of one of these shapes. So we have a structure that's approximately 25 millimeters in diameter. And we have ourselves some radial coordinates that we can start calling out, because this is like a globe. And if you think about a globe, you can kind of draw a line from the center, which is that circular part here. And if you just drew a point out in space, you could describe that point in space by a radial angle theta. And so here we have on the left side a small circle that has S of M and S of R. The S of M is the minimum distance from that random point that we've just selected, that arbitrary point. It's a random location, but it's the minimum distance from the outside of this Tootsie Roll Pop to the soft center. So that's S of M, and that's going to be important later. We also have another variable, S of R. This is the distance really to the center of the Tootsie Roll Pop. And so you can see that this distance is some length that's dependent on the orientation of this lollipop with respect to this initial point. You could see that the distance to the center might change if you have moved around on this object. Already makes sense so far? So we're really diving deep into the structure of asymmetric composite materials here. Okay, so the next thing we got to do is start unwrapping this problem, because if you were to just take one of these Tootsie Roll Pops, take a cross section, you'd understand pretty well where everything is. But let's say you want to do this over many, 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 many lollipops. You want to get an average. You want to know what the statistics are between all of these different Tootsie Roll Pops. So here I've drawn on the left a series of like a grid, really. It's a grid again showing dimensions. And the dimensions of this lollipop now have multiple lines around them. And this really shows that among all the lollipops that we've tested, you have an average profile, which is your straight line. And then around that straight line on that outside perimeter, you have these two dashed lines, one inside and one outside. And that gives you plus or minus one standard deviation away from that average surface profile. And that kind of gives you a sense of just how much the size of the lollipop changes when you cut 50 of them in a row and you image them and you trace them by hand. It's a painful process, but it has to be done in the name of science. And so here you have, again, the soft center, which has this average tracing. And here, of course, we're only showing one drawing. If I tried to overlay all of the different schematics, it would look like a blur. So I'm not trying to do that. I'm just trying to extrapolate all the statistics that we've learned from cutting open each one of those lollipops and basically transposing it or putting it, overlaying it onto one of our Tootsie Roll Pops. So you can get a sense of just how much it fluctuates. You can see that the hard shell has pretty decent tolerances, and tolerances are a way that we can kind of describe the variability between parts. So if you're producing a part in a factory and you have very tight tolerances, that means that you have to hit the same value every single time. If you have very loose tolerances or very high, very open tolerances or no tolerances, you can have shapes that change very dramatically between parts. So it looks like the outside of this very hard candy has tighter tolerances than the soft center inside. And that's probably because of the process that was used to manufacture this piece of candy. But you see here, these edges of the candy, this is a part of the mold. This is actually a mold that's pushed down, and the hard candy is actually basically cured, or not cured, but it's hardened within a mold. And that mold is rigid. And so you can imagine that the uncertainty or the standard deviation around that mold is going to be a lot tighter. It's going to be a lot smaller than that soft center, which is gooey, and that's just injected. It doesn't have a lot of tolerances. It doesn't have a lot of precision in where that's placed, which is another reason why you see it's very irregular when you cut it open. You can see that there's a lot of flow almost, and it's a beautiful system. Okay, so now we unwrap this. If we were to kind of unwrap this entire surface, the outer surface only now, and if we were to take points A, B, C, and D along this perimeter, and we were to unwrap it, you'd see that this is really the fluctuation. This is really this is how the surface topography kind of looks if you're unwrapping it. This is how much it changes. And again, we're looking at plus or minus 1 standard deviation in the dashed lines, and the solid line is the average. And your S of M is going to be the minimum distance to your soft center. Okay, and again, we're using angular coordinates here, but that's just showing you along the entire circular shape. This is how the profile is changing. Okay, so now, what does this have to do with my research? So the interface between yourself and a lollipop is a biological interface. You are a part of this interface. It is a material that you are trying to consume. And so part of, I think, the magic of the lollipop is that it's a model for something called BioTribo corrosion. So everybody's heard, I think, of corrosion. Corrosion is a process that you find all over the place. You'll find it between metals that are in contact or that are in like a marine environment. If you see anything rusting, that's a corrosion process. Corrosion happens everywhere. But it can also happen in the body. And this happens oftentimes when there's a metal implant that's been put in the body for a medical reason. For instance, like I've shown here, where you have a metal implant. And tribocorrosion is the process of corrosion that's accelerated and kind of induced by friction and wear. And so here we have a hip implant, which is a metal on metal contact, which was one of the big no-nos in the field of tribology, which is the study of friction, wear, and lubrication of sliding interfaces. When you have two metals in contact, they're going to rub against each other. And because of the hardness, how stiff they really are, there's not a lot of compliance. So anywhere they touch, they're going to be very high contact pressures, very small contact areas. And whenever you have those types of conditions, sometimes you can have wear particles that are generated. All this to say, the lollipop is kind of like the implant, where it's a hard surface sliding against something that's softer, in this case, our tongue. And this whole study that I'll be illustrating to you is supposed to help you understand the chemical and mechanical contributions to material removal and wear in a biological environment. So this is kind of an allegory. It's not the same. This is a metaphor in a way of the BioTribo corrosion processes, but we can essentially use the lollipop as a model system for these lessons here. So I talked about a few types of words just now. I said elastic modulus, I said stiffness. Let's talk about what that really means. So elastic modulus, for those of you who haven't heard what that means, it's essentially the stiffness of a material. And here I've laid out a picnic. I know some of you really like picnics, and it's a good socially distant activity to do. So what you can do on a picnic is go through the materials that you've brought to your picnic, and you can kind of get a sense of the orders of magnitude of elastic modulus in your system. So here on the left, we have glass. And glass has an elastic modulus, which is given by E of 100 gigapascals. What does that mean? That means it's very stiff. That means if you were to touch it or push it or try to push on it, it's going to have a lot of resistance. It's not going to want to deform. It's not going to want to become compliant in response to that force. So here I've shown what this really means visually. So your elastic modulus is going to be given by some units of force divided by an area. So here we have some undeformed cylinder of some height h, of some cross-sectional area A, that's just your area. And if you are subjecting this material to a force, you can imagine that at some length scale, maybe you won't be able to see it. Sometimes this happens at micron scales or nanoscales, but at some scale, there will be some kind of deformation. And that deformation is given by a change in height. Here I've got delta height, or change in height, from the initial to the final position. And so here, under the force, you have some deformation. So the pressure in this system is given by the elastic modulus multiplied by the change in height divided by the initial height. So here we can get a sense for what this means. If we have a very stiff material like glass, it's not going to want to deform all that much. If we have something like salmon roe, we're going to have something that's about 20 kilopascals, which is much softer, orders of magnitude softer. And here on the right, I've given you all the different orders of magnitude that you might find on this beautiful picnic table spread. So you can see that you've got your metals and glasses at the very top, and you've got your salmon roe, and you've got gels and cheeses at the bottom. And so I want to give you a sense of the types of language we might be talking about later. Okay, so that's one part of the story, the stiffness of a system. The second part, naturally, is friction. There's got to be some kind of a interaction between two sliding interfaces. Obviously, you're not just putting the lollipop in your mouth and letting it sit there. You're actively working it. You're mechanically agitating that lollipop. You are participating in a BioTribo corrosion process. So what does it mean? What does friction mean? So when I think of friction, I think of a resistance to motion. And in this left-hand quadrant that I've shown here, we have a block, just a simple block of some known material, and it's sliding against another material. It's this platform down here, you can see. So friction requires the interactions between two materials or more, two or more materials, but you need to have two materials. And this material, this block, is in contact right here. So you can see where the cross-sectional area, really, the area of contact it's called, is shown. And so if this block was just in simple static contact, you'd have a normal force given by Fn divided by a contact area A, which gives you pressure. We remember that from before. However, when you're starting to slide that object against that flat material or that flat portion here, it's going to have a resistance to motion because there's always a penalty for sliding. There's always a penalty. And so this F of F is the force of friction that when you divide by the normal force becomes your friction coefficient. The higher your friction coefficient, the more the material that you're sliding wants to resist motion. So think about a cork. The cork is going to be a material that you find all over the place. Usually it's in wine bottles or it's on your coasters. Imagine taking that cork and trying to slide it across the fabric. It has a very high friction coefficient. The friction coefficient is 1. Sometimes it's even higher. Rubber on the ground. If you have a rubber eraser and you're trying to rub it against the paper, it has a lot of resistance. You've really got to work it. So the higher your friction coefficient, the higher the interaction, the higher the resistance to motion that you have. So again, some orders of magnitude on your picnic table. You have rose petals against your finger, let's say, has a friction coefficient of 0.1. That same rose petal under its own weight, just sitting on a table, has a contact pressure of about 1 kilopascal. So why am I emphasizing this? because it turns out a lot of biology exists in this regime, of this 1 kilopascal regime. So here, our tongue sliding against our lollipop is also applying similar contact pressures because our tongue is soft and the lollipop is very rigid. And so we have a very high contact area. We have a lot of contact between our tongue and our lollipop. And so the contact pressures are only about 1 kilopascal. The tongue itself has an elastic modulus, stiffness, of about 15 kilopascals. So similar to that salmon roe that you were thinking of earlier. And so when we apply a force, about 3 newtons of load, essentially on our lollipop with a very high contact area, you drop those contact pressures and you have a very high contact area. Okay, so enough of this. Let's continue to the good stuff. So we are not the first to think about this. We are not the first to do this experiment. We're not the first to do any of this. People have done this before. They have certainly searched for the answers, which is how many licks does it take to get to the center of a Tootsie Roll Pop? So you can see a lot of different universities have tried this. And in fact, they've even built machines to do the licking for them. So the red or the coral colored bars indicate that the test was involving a machine simulated licking or a licking simulator. And here's a schematic of one in case you've never seen one of these. It's essentially a lollipop held horizontally, and there's a motor that is essentially rotating a series of sponges, which is supposed to simulate the mechanical properties of the tongue. And presumably they soak the sponges so that it also has a similar type of effect. Now, people have also tried it with humans. So all the blue bars are licking experiments that humans have done. There's one really cool experiment that the New York University has done, which is a flow-based model to see if flow is really driving material loss. And so this is how they were simulating the number of licks. So yeah, we've got a lot of different numbers here. You can tell right away that you've got many orders of magnitude of range of numbers. You've got 144 on one end of the spectrum, and you've got over 3,000 on the right. And presumably, these are all scientists, right? These are all graduate students. These are all people who really care about making careful measurements. So what do? Well, we don't go with graduate students. We don't go with scientists. We go with students from high schools and middle schools. So this was a STEM camp. This was an outreach. This was a really fun experience. This is me on the right side, speaking with a bunch of really quite talented tribologists. And what we did was we took a whole mess of Tootsie Roll Pops. We provided students with little tins that they were to put their Tootsie Roll Pop on top. You can see here. And we gave the students some very small balances, digital balances, and we instructed them to record their licking style. We didn't tell them what to do. We just said, we would like you to take as many licks as you want, but then intermittently take a mass measurement or weigh that lollipop to see how much material loss has occurred from your process. And so here you can see a student taking a lollipop, setting it down onto that tin, and letting the balance record what kinds of volume or mass loss or weight loss took place. Another fancy trick that we brought to the STEM camp was a 3D point cloud based approach where we took volumetric measurements. We essentially just took a 3-dimensional scan of the lollipop as well, so that intermittently you could see how the volume was changing as a function of how many licks. And we hoped that with enough students and with enough enthusiasm, because I certainly didn't want to go through all these myself, we would find the answer. So what causes volume loss in lollipops? This was the big question. And a hint came to us.
How many licks does it take to get to the roll center of a Tootsie Pop?
one of the first things we thought of was going back to that commercial and going to the very end and saying, well, okay, so the way that these lollipops seem to diminish in size, maybe it's due to a dissolution process. Maybe they're just dissolving because we're licking them and it's a very moist environment in our mouths, and maybe they're just dissolving. But maybe it's because our tongue is very rough. In fact, what we did in the lab back in Florida was we molded our tongues. We took some silicone, and this is like a medical grade silicone that's used to mold braces and everything. So we stuck our tongues into little tiny containers of silicone, and then we poured epoxy into the mold, and we removed the mold, the epoxy, the negative really, and we saw that the tongue is extremely rough. We measured the surface roughness, and it's 33 micrometers, the average surface roughness, which is really, really rough. To give you a sense, a mirrored finish of something, if you look at a mirrored surface, that has a surface roughness of about 100 nanometers. And so this is an order of magnitude, 2 orders of magnitude greater than that. So you're comparing basically a flat sheet with like concrete from a road, essentially. So we have a very rough tongue. So maybe it's abrasion. Maybe the abrasion is what's causing it. I think I see a question in the chat. Could somebody call out the question, please? I'm afraid if I minimize the screen, I'll lose everything.
Angela, let's do the questions at the end.
Oh, sounds good. How am I doing on time?
It's 4:59 right now, so a few more minutes.
Perfect. So what is the volume loss due to? We had a lot of different hypotheses. Oh no. So what we did was we asked the students again to perform the licking and weighing experiments, and also to measure the volume loss. When we asked them to report their findings, what we found was quite remarkable. When we looked at the way that the students were describing their licking styles, it basically fell into 2 camps. There was the students who decided to have one-sided licking, which is they just held it in their hands and just licked it. And then there was this set of students who put it in their mouth and swirled it around. And maybe one of you, maybe you have maybe you're partial to one or maybe more of these methods. We also noticed that towards the end, there were some outliers. About 21 students reported about 100 milligrams of volume loss, mass loss per lick. We suspect that they might have been biting them. But that's again, we don't know, we just have the data, and this is what we have. So we have reported average and standard deviations, and we have about, in all, many lollipops that we went through. This is about 300 students who decided to do the one-sided licking, and about almost 200 students doing the full surface. And again, we didn't try to select for any of these students. This is just what they reported. And so when we do the measurements of the initial, the one-sided, the full surface, when we do the statistics, we have to now use a Monte Carlo simulation to really figure out what the statistical averages of these surfaces might be, so that we can get average wear rates. So here we're showing equatorial depth. This is just the depth into the material that we're going around the center. And if you take a look, the full surface and the one-sided styles are almost the same initially, up until around 150 cycles, and then they start departing, which is really quite amazing. So the one-sided licking style really affected a smaller percentage of the Tootsie Roll profile, which makes sense because you're only impacting one side. So here was another hypothesis we have. Maybe it's dissolution. But when you stick a Tootsie Roll pop into water, it takes you the age of the universe to dissolve it. It's much faster to eat these things, and it's much more delicious too. But when you try to have a dry mouth and you try to lick it without having a lot of saliva in your mouth, this is actually not a very effective process either. And you have very low volume loss per lick. So the saliva is actually a really important process as well. It's part of the process. So we did some models. I'll kind of go ahead just so you guys can get to the end of this and figure out what was the number that we come up with. But we did multiple models. So here's a spherical segment model where we take a circle and we begin making slices towards one side. This is kind of modeling our one-sided licking style. And you can see that this is the depth into the material, and this is our volume loss as a function of numbers of licks. This is another more elevated kind of style where we have a spherical model now, and now we're taking kind of spherical capped sections, depths of cut into the material. And you see that again, the numbers of licks increase as you increase the depth of cut. We also have, for the people who did the full surface types of licking styles, we have these shell models. So if you took a shell and you began taking cuts that were a single ring down, you'd start to see that the numbers of licks, again, you'd have a much higher depth of cut with numbers of licks. This is our model here. And so the wear prediction, again, this is based on many thousands. We did 5,000 Monte Carlo simulations to just figure out this model. And the maximum penetration depth into the Tootsie Roll Pop seems to be a global minimum around 130 licks. So this was really our answer, where 130 licks is all it takes to get to the center of a Tootsie Roll Pop on average. Again, there are a lot of variability here. So you might someday have a lollipop and you might be lucky and you might get very close to the tip of that soft center. But on average, we get 130 plus or minus 29 licks to get to the center of a Tootsie Roll Pop. With that, I just want to thank all the students who were involved in this. They really took many for the team, and this was all done back in the old school back at University of Florida, and I want to thank everybody who's a part of that. Any questions? I'd be happy to take your questions.
Great. So everybody, please join us in thanking Angela for this really nice talk. And